Okay, so I think we can start with the last talk of the afternoon by Shota Komatsu about Coulomb branch and the integrability.
All right, so thank you for the introduction, and also thank you for the organizers for putting together this wonderful work conference. So yes, today I'm going to talk about our recent work together with Frank Coronado and Costa Zarambo about Coulomb branch of N equals 4 supermills and integrability. And let me also mention that when we started this project, we were also discussing a lot with Clay Cordova, so like a special thanks to Clay as well. Well, Clay, yeah, I didn't put his name here, but okay. All right, so let's start with some motivation and introduction. So this is the 21st edition of IGST. So finally, IGST became old enough to drink alcohol. So, well, in the US. So we have seen impressive progress over the past years about N equals 4 supermills, planar N equals 4 supermills. For example, like exact computation of the spectrum, and then non-perturbative results of amplitudes, correlation function, and also various kinds of defects. But I think it's worth reminding ourselves why we were so excited when we first found that N equals 4 supermills might be integrable theory. So one of the reasons why it was so exciting was because there was some precursor to all these developments, which was actually found in the actual QCD, especially in the high energy limit. And in particular, it was found in the so-called BFK limit, and it was formulated by Fadeev and Korchemsky as a kind of integrable spin chain, describing this high energy perturbative regime of QCD. And also, I should also mention that this idea of using integrability to study Yang-Mills theory, like actual Yang-Mills theory or QCD, is also something Feynman really wanted to do just before he passed away. So which you can see from this Feynman's last blackboard, and you can see this beta ansatz. And also you see that he writes a note, he wants to know how to solve theory, or well, anyway, yeah, I'm not sure if I can read. Okay, so yeah, so then it's worth asking this question again, probably. Can we use integrability to learn something about QCD or Yang-Mills? And well, we have seen already a nice result, especially in this BFK limit of N equals 4 supermills, thanks to many people in the audience. So the point is that the BFK limit of N equals 4 supermills captures the most complicated part of the BFK limit of Yang-Mills theory. And you can actually derive and systematically extend the BFK result, which was obtained before, using sophisticated techniques like a quantum spectral curve. And also, there is another completely different appearance of integrability recently in the context of QCD flux tube, found by these people. And we will hear something related from Barak tomorrow, I guess. And in addition, if you go down to 2D QCD, there is some emergent interesting structure found by these people. So what they found is that you can actually write down a Q system or Q functions which govern the meson spectrum in 2D QCD. And so today's talk is to propose yet another way of making N equals 4 supermills a little bit closer to the actual Yang-Mills theory or QCD, which is to study the Coulomb branch of N equals 4 supermills. So the Coulomb branch of N equals 4 supermills has an advantage, is that studying them allows us to break conformal invariance while actually maintaining the full quantum integrability that we already found in planar N equals 4 supermills. And furthermore, going to the Coulomb branch allows you to introduce the mass scale to otherwise conformal theory. And having a mass scale allows you to study various kinds of new observables. For example, the vacuum condensate, which is basically a one-point function of local operators, or something like a meson spectrum. Precisely, it's actually W boson bound state. And also scattering amplitudes of mesons. And we'll hear something related from Elisabetta tomorrow or maybe day after tomorrow. Okay, so that's kind of why studying Coulomb branch of N equals 4 supermills may be interesting. And of course, just studying each of them doesn't allow you to really study Yang-Mills theory, but the hope is that by studying all these aspects or all these different regimes, maybe you can learn some lessons that apply also to actual Yang-Mills theory or QCD. well, at the end of my talk, like I will also mention yet another possibly more interesting setup, especially I will mention that in the last slide. Okay. So let me just like explain more clearly what's the setup of Coulomb branch of n equals 4 supermos. So Coulomb branch basically means that giving a kind of web to one of the scalars in n equals 4 supermos, and then go to some regime in which like gauge symmetry is spontaneously broken. And there are different ways of doing it, but the one that I'm going to talk about today is the one in which UN gauge symmetry gets broken down to U1 times UN minus 1. So this can be achieved by turning on this kind of web in one of the scalar. So you just like turn on one component. Okay? So from the D-brane picture, that means that you have like n D-brane, and you just separate one of them. And the distance between like n minus 1 brane and this probe 1 brane is given by this number v. Okay? And you can also kind of like consider the holography for this setup. And what holography means in this setup is that you basically replace this stack of n minus 1 brane by some ADS geometry. And if you do so, you are left with this like a probe brane. So now you have some ADS 5 times S5 spacetime with a probe D brane. And then probe D brane sits at the z coordinate, which is like inversely proportional to the expectation value. Okay? And in this setup, perhaps one of the simplest observable in this context is one-point function of local operator. So of course, like a one-point function vanishes if you preserve conformal symmetry, but now because you broke the conformal symmetry by introducing a vacuum expectation value, so now you can study the one-point function. And especially, let's consider the one-point function of a single trace operator. And so that is holographically given by some like a closed string emitted from the boundary. So that's like where the operator is inserted. And then this closed string worldsheet gets absorbed by this probe D3 brane. Okay, so this is a space-time picture of this one-point function in holography. And from the worldsheet point of view, this is just nothing but the overlap between the closed string on-shell state and the boundary state corresponding to this probe D3 brane. Okay? And the punchline of my talk is that this boundary state is actually what's called integrable boundary state, which has a very nice property, and you can actually determine this boundary state explicitly at finite to foot coupling using integrability. And using the structure of the boundary state that you determined, you can even kind of like write down some finite coupling answer for this one-point function, which takes this kind of like a horrendous form. And I'm going to explain each of the ingredients in the rest of my talk, okay? So this like the important part is like these three like parts, and this determinant is what's called like it's some super determinant of what's called Gordon matrix. But this Gordon matrix is some matrix whose element is a logarithmic derivative of the beta equation. So once you know the beta equation, you can write it down. And whereas like this part, which is a complicated function, which depends on the rapidity of the particle, is coming from the reflection matrix that describes the boundary state. And finally, there is some interesting kinematical factor. So let me explain these three elements one by one, and like that basically fills the rest of my talk. So let's start with the superdeterminant of the Gordon matrix, okay? So to see the emergence of the superdeterminant or why it's important, you can actually see it already in the weak coupling. And precisely speaking, you can actually see it already at the tree-level computation. So how do you compute one-point function of a local operator or vacuum condensate at tree level of n equals 4 supermos? Well, that's very easy. You just write down the operator and replace the operator with its expectation value, which is just given by this. So this is a kind of like a simple field theory analysis, but you can also rewrite it in terms of the spin chain language because we already know the map between the single trace operator and the spin chain thanks to the works by many people. And for example, if you consider operator made out of just scalar, like a 6 scalars, which we call SO6 sector, and this can be expressed as a spin chain overlap. So this B is a particular boundary state whose vector is basically given by the like a direction of the vector of the vacuum expectation value. So this is a kind of like a trivial rewriting of the field theory computation into the spin chain language. But what's surprising is that this boundary state is known to be what's called integrable boundary state, and in particular, it is annihilated by infinitely many like higher spin conserved charges that exist in the integrable spin chain. And using that property, people already actually derived analytically that you can actually compute this object overlap in terms of this kind of like a formula. And then this here, you can see the superdeterminant. So the details of the formula is not that important. It's like for those who know the subject, like it's obvious. It's just like a logarithmic derivative of the beta equation. For those of you who don't know, like I don't have time to explain. So, but okay, but you can at least have a feeling of what it is. And so this is a kind of like tree-level answer. And so now, of course, like this is just a tree-level answer. And the nice thing about this part, like the superdeterminant part, is that we also know the finite coupling generalization of this Gordon superdeterminant. Because like we know the beta equation at finite coupling, thanks to like Nicholas, Matthias, and other people in the audience. But what's not obvious is how to generalize like other parts, like especially like this part, which is given by what's called Q function, which depends on some rapidity of the operator. Okay? So that's the next thing we need to figure out, okay? So that brings us to this next part, all right? So, and the punchline here is that this complicated part is actually coming from the structure of the boundary state, okay? By the way, how much time do we? 20 more minutes, okay. All right, so let's talk about the next part now. So as I said, like I mentioned that like this part is related to the like a structure of the boundary state, or more precisely, what's called a reflection matrix. To see that, like let's consider like overlap between the boundary state and then two particle state. One magnum with momentum u and the other magnum with momentum u bar. So here u bar is actually minus u. So pictorially, like this overlap, you can think of it as a process in which like two magnum states gets absorbed by this boundary state here. Okay. So this at this point doesn't look like a reflection matrix, but if you rotate this picture by 90 degrees, then you can see that this is actually nothing but the reflection process in which like a magnum with momentum u gets reflected by the boundary, and you get magnum with momentum minus u. And so, of course, like this rotation, well, you can understand it pictorially, but if you want to be more rigorous, you can do it by what's called mirror transformation. And the key point here is that this reflection matrix, you can actually bootstrap at finite coupling by imposing various consistency conditions, which I'm now going to review, okay? So what's the first consistency condition? So the first consistency condition is the symmetry requirement. So if you consider some symmetry generator G, which is preserved by this Coulomb branch configuration, then this boundary state needs to give 0. So the boundary state needs to be annihilated by the symmetry preserved by the Coulomb branch. And this symmetry generator in this case, is basically like a supersymmetry generator inside a PSU2/2 square, which Nicholas talked about yesterday. Because like the Coulomb branch of n equals 4 supermills preserve all supersymmetry but breaks all superconformal symmetry. So you just like pick the supersymmetry part of the PSU2/2 square and require that this boundary state is annihilated by this symmetry. And so this is a kind of straightforward exercise because we know how the symmetry generator acts on magnum, again thanks to Nicholas and other people. And if you do this analysis, you discover that actually, like this two-particle overlap is almost uniquely determined. So especially the tensor structure is uniquely determined, and what's undetermined is just the overall function. And that this tensor structure is basically given by this kind of expression. Okay? And so what's left for us is to determine this overall unfixed function. And in order to determine this unfixed function, we need to use other conditions. So what are other conditions? So one condition that's important for us is boundary Yang-Baxter equation. So the idea is that in the tree level, people have shown that the boundary, like a state corresponding to the Coulomb branch, is actually integrable boundary state. But at finite coupling, of course, we don't know whether it's really integrable boundary state or not. But let's just assume that it's integrable. And if it's integrable, it needs to satisfy this kind of like what's called boundary Yang-Baxter equation, which is the boundary analog of the Yang-Baxter equation. And however, like it turned out that this equation is not useful for determining overall factor, because like irrespective of this K of U, you can actually show that this tensor structure guarantees that this equation is satisfied. So this is a little bit like similar to the situation of the bulk S matrix. So you can actually determine the 2 to 2 S matrix just by imposing the centrally extended PSU2/2 square symmetry. And as a result, you discover that S matrix actually automatically satisfies the Yang-Baxter equation. Okay. So in some sense like this, you can think of this as an indication of integrability in the Coulomb branch, the fact that this automatically satisfies it. And in order to really determine this K of U, you need to use other conditions. So the condition 3, what's called Watson equation, and then condition 4, what's called crossing equation. So this Watson equation basically means that if you like swap the order of particle, you need to multiply the S matrix. And that leads to a condition which looks like this. Like S matrix times K of minus U is equal to K of U. Whereas there is another condition which is called crossing equation, which basically means that if you have like a 2-particle antiparticle pair, it's equivalent to doing nothing. So there is a similar equation for the usual S matrix, and this is a boundary analog. And that leads to this kind of equation, okay? So now our task is to basically like solve these equations. So like in the previous slide, I only like wrote like a schematic equation, but this is the actual equation that we need to solve. And this is actually a complicated equation. For example, this is a dressing phase, which is a super complicated function of the rapidity. And also like this equation involves certain analytic continuation of this parameter U, because like this U is known to live on the branched surface, and then this U to gamma requires to go to the kind of like go through the branch cut twice, okay? So this is a complicated equation to solve, but fortunately, what we found is that actually I together with Ifan 1 already solved related equation in the context of defect one-point function. So it turned out that these equations just happen to coincide with certain limit of the equation for defect one-point function, which we studied a few years ago. So we just took the answer and then took the limit. And so this is the answer. And as a result, we get this kind of answer. So that this K of U is given by this expression. Okay? So these are what's called Joukowsky function, and then this sigma is a dressing phase. And then this sigma b is the new part, which is given by this kind of integral representation. And once you have this expression, you can also like explicitly check that these equations are satisfied by this integral representation. And furthermore, you can also do the weak coupling expansion and then see that this like a new part sigma b produces this kind of interesting expression, which contains like a Euler-Mascheroni function, a constant. Okay? So combining these two, we can explain like everything inside a square root. And what's left for me to explain is the last one, which is called the kinematical factor. So let me explain what that is in the rest of my talk. So these kind of structures already appeared in other contexts in which the D-brane shows up in the context of like a one-point function, for example, like a defect one-point function or a heavy light three-point function. However, in the context of Coulomb branch, there is one new ingredient, which is precisely this kinematical factor. And so the reason why we need this new ingredient is because of the following. So in the spin chain description of the single trace operator, highest weight states of superconformal algebra correspond to spin chain states with finite rapidities. And if you want to consider non-highest weight states, then you need to consider spin chain states with infinite rapidities. And it turns out that on the Coulomb branch, only non-highest weight states have non-zero VEV. And the highest weight states have actually zero vacuum expectation value because of the symmetry reason. So we are forced to consider like some spin chain states with infinite rapidities in this context. However, like the formula that I showed, which was derived also in other contexts, were only valid and only checked for highest weight states. So we need some kind of like a kinematical factor which accounts for the difference between highest weight state and non-highest weight state, or superconformal descendants. And so this is not something people have derived before or people have studied before. So what we did was to study the tree level in detail and make a conjecture for finite coupling, okay? So let me explain what we did at the tree level. So at tree level, what we did was the following. So as I already mentioned before, like at tree level, like it amounts to computing some kind of overlap in the SO6 spin chain if you consider operator with just scalars, and we know the exact answer. And so this SO6 spin chain is some kind of subsector of full PSU22/4 at one loop, and it can be embedded into what's called beauty grading, okay? However, it is also known that this particular like a grading of PSU22/4 actually is not very compatible with the finite coupling spin chain description, like a finite coupling beta ansatz description. So this is related to the fact that SO6 sector is not closed subsector at finite coupling. So in order to kind of make a conjecture at finite coupling, so you need to do a fermionic duality transformation starting from this expression. And if you carefully follow the fermionic duality transformation, you discover that in the new grading, which extends, so for example, this grading, alternate grading, which extends to finite coupling, the states you started with now become superconformal descendants in this grading. And furthermore, you can very carefully follow the fermionic duality transformation studied by, for example, these people, and derive that there is an extra factor coming out if you follow the fermionic duality transformation. And these Ks are basically like a number of magnons at J's nodes. So this is a kind of exact answer for the kinematical factor at tree level. And now we make a conjecture that we replace this K, which are magnon numbers, by some related quantum numbers, because magnon number itself is not really a kind of like a good quantum number. And we replace Ks by related quantum number. Well, so of course, like strictly speaking, there is no precise logic here. We are just making conjecture. But it works. The important point is that it works. Okay, so, and then once you make this conjecture, sorry for my voice, and putting together everything, then you can actually reproduce the direct one-loop computation in field theory, for example, like so this is like a dimension 4 operator in the SO6 sector. But now, like the final answer at one loop takes a complicated form. And in the field theory, on the field theory side, computing this is actually very complicated because you need to diagonalize the two-loop Hamiltonian, which also induces a mixing with fermions and gauge fields. But we managed to do the computation, or more precisely, Kostya managed to do the computation, and then this is the answer. Okay, so, and indeed, like this is precisely reproduced from the integrability prediction, and especially like this sigma b reproduces nicely this Euler-Mascheroni constant. Okay, so I guess how much time do I have? Okay, so we have plenty of time. So let me conclude and then mention prospect. So the main message of my talk is that Coulomb branch is integrable, and the boundary state can be explicitly constructed. And using the explicitly constructed boundary state, you can actually make a prediction about the one-point function at finite coupling. And technically, what was new as compared to like other related contexts is that you need to multiply some kinematical factor in order to account for like a difference between superconformal primary and superconformal descendants. And so there are several like future directions. Like one kind of like immediate thing one can try to explore is this like a generalization of a kinematical factor. So I didn't emphasize that very much in my talk, but like the kinematic factor, we basically only studied for certain SO6 operators. So we don't even have a conjecture for most general operators. So understanding the actual origin, or maybe coming up with some precise derivation would be ideal. And other interesting directions are like studying other observables on the Coulomb branch using integrability. For example, form factors or amplitudes of mesons. So let me mention that the form factor here is different from the form factor people already studied, because like so there are like a bunch of nice papers about the form factor of n equals 4 supermills, but these form factors are basically the form factor at the conformal point, and then they are genuinely different from the form factor in the Coulomb branch. And another interesting question to ask is to see whether there are other massive integrable theories in 4D or 3D. And one kind of like easy goals are basically probably massive fishnets or fishnet with spontaneous symmetry breaking studied by these people. And it'll be nice to kind of like study, for example, meson spectrum and so on, or one-point function in these series. But there is also yet another interesting theory which I wanted to highlight, which is this mass-deformed ABGM theory. So this theory is very interesting. So in n equals 4 supermills, if you do the mass deformation, you break some part of the supersymmetry. But ABGM is different. Like there is actually a mass deformation which preserves all the supersymmetry. And furthermore, like if you do the mass deformation, you get a very interesting algebra, which is actually the centrally extended PSU 2/2 symmetry, which was nicely discussed by Nicholas yesterday. And yesterday, Nicholas mentioned that there is some kind of like a three-dimensional structure, there are like central charges look like a three-dimensional momentum, but in this theory, this three-dimensional momentum are really the three-dimensional momentum of this theory. And this was also found by Nicholas and his collaborators. And so this importance of this theory was emphasized to me many times by Clay Cordova. But for a long time, I was thinking that this is just a mathematical coincidence. But last year, there was this paper by Charlotte and other people, which pointed out that actually, at tree level, if you consider one-point function in this mass-deformed ABGM theory, it can be mapped to some kind of like integral boundary state computation. So I will be still surprised if the integrability persists by this mass deformation, but at least there is some hope that this mass-deformed ABGM theory may be integrable, and it might be actually, if it's really so, it might be the first like a massive integrable theory in higher dimensions. Thank you very much.
So that formula, main complication is about the operator structure. The coupling dependence apparently is trivial. It's like normalization.
Sorry, like this formula?
Yeah. So my question is actually, you didn't mention ADS5S5. So suppose how you see this result on string side, for example. So you put D3 brain probe in ADS5S5. What you do next? How you get this coupling dependence and
Okay, so the first thing I should mention is that the coupling dependence, the explicit coupling dependence only appears here, but like these are Joukowsky variables, so it secretly depends on the couplings.
Okay.
So
So
it's a very complicated function of coupling.
Then my second question becomes relevant. So if you take large G, what happens then?
Yeah, that's an interesting question. I think we didn't study them. So there are several interesting regimes one can explore. One is to go to the short string and then compare with some flat space computation. And another is to consider some like a macroscopic string and then try to construct some minimal surface ending on a D3 brane. And both are interesting questions which we didn't explore.
So you were saying how the nice thing about ABGM is that you could turn on the mass for this U1, which preserves all the supersymmetry. Is it known in n equals 4 that if you turn on the mass that you don't have integrability?
It's not known either. Again, like I would be highly surprised if it remains to be integrable. But yeah, that's my answer. Okay.
Yeah, I mean, I guess the reason why I was asking is that 40 n equals 2 gauge theory I was telling you about, of course it has masses that preserve the supersymmetry. So if it's to be integrable, or it's just,
right.
n equals 4 the mass would be integrable.
Yeah, well, I think, right. Yeah, I think it's also interesting to think about, indeed, like a mass deformation of n equals 4 supermass.
I think Volodya wants to ask a question.
Yes, I can repeat the question. Yes. Okay.
Question from above.
An actual question is, of course, the path to TBA, like finding the mirror solid state,
right.
etc. Please comment.
Yes. So yes. Thanks for the question, because that's one thing I didn't emphasize. So this is the equation, this is the expression for asymptotic limit, and you need to correct them by the TBA. And we have some, for the like a heavy light, like a determinant single trace 3-point function, we have some like a proposal of how to use TBA to correct them. And for this one, we don't have a proposal, and that neither is true for the defect 1-point function case. And the reason is that you can try to write down some kind of Fredholm determinant which generalizes this superdeterminant. But in the Coulomb branch case and in defect 1-point function case, that Fredholm determinant just gives infinity. And you need to do regularization. And we don't know how to do it. But for the case of heavy light 3-point function, that Fredholm determinant turns out to be finite. So in that particular case, like the proposal does make sense, but we didn't do extensive tests.
Is it the first physical absorber which depends on earlier gamma explicitly?
Well, actually, defect 1-point function, also in the defect 1-point function, this shows up.
Okay, other questions? Yes, Andrea.
The generalization of the superdeterminant, it's something that depends only on the y function of the state, but not on the boundary state. So
that's true.
Why is it finite or not finite depending on?
So it only depends on one function of the state, but like how you take Z2, so in order to define like a superdeterminant, you need to introduce a Z2 grading structure. And that Z2 grading structure is dictated by the symmetry of the problem. And for the heavy light, basically Z2 is like a Z2 which exchanges 2 wings. So that like infinity cancels between like a determinant plus and determinant minus. But that's not the case here.
Thanks.
Okay, so if there are no other questions, let's thank Shota again. And see you at the poster and at the reception later this afternoon, this evening.